Today we'll be continuing from before. We will be trying to work with certain binary operations and see whether we can call them binary operations. So let's look at the first sum that we have here. It says A dot B equals A minus B. So they have defined an operation dot in a way such that A dot B is A minus B. So as I've mentioned before, you can define your operations in any which way you like. It could have been any way that they could have defined. They particularly want us to find out whether this dot operation defined in this following manner can be called a binary operation or not. So that is what we need to find out. And also, since I had mentioned before, for every operation to be considered as a binary operation, that is, before we even start finding out whether that operation can be called a binary operation or not, we need to know the set on which the operation is defined. So we need to know the area on which this binary operation walks upon. So the sum says that this binary operation is defined on the set of natural numbers. If you've forgotten about what natural numbers are, they are essentially the set of all numbers that can essentially be counted. So that's an easy way to put it. Essentially all numbers which we can count are natural numbers. So since we essentially cannot count zero, if I give you zero things, or if I give you zero toys, you won't be able to count it. So zero is not a natural number. You need to remember it this way. 1, 2, 3, all other positive integers are essentially natural numbers are the set of positive integers. So that's how you remember what natural numbers are. Now let's look at the first sums. So I've listed all the 4 sums here at the same time. We'll be taking it one at a time, and let's look at the first sum. So we have the solution of the first sum. What I do is, by the definition of binary operation, this A and B, when operated on each other, need to map to a particular element which still exists in the natural number. So as I had defined before, essentially a binary operation is an operation which maps elements from a set to a set. So since they have defined that the operation is essentially works on the set of natural numbers, and I have defined natural numbers just now, essentially what they mean is, let's say that I have an element A and B in the set of natural numbers. What happens is, when I operate these two elements, it maps to an element, let's say A dot B, which again is in the set of natural numbers. So the first thing that I need to check by definition is whether the set under consideration is empty or not. So that solves from the definition itself, because the set of natural numbers is not an empty set. It has elements, essentially 1, 2, 3, 4 and all, countably infinite set of positive integers. So that's not an empty set. The next step that we move to is, we need to find out whether the resultant of the binary operations are in the set or not. So another thing that is very easy to remember is, when we need to prove something, we need to prove it in general for all the values that we have. But if we need to disprove something, one specific example in which the given situation does not work out is sufficient. So in this case, if you see the sum, you will understand that we essentially need to disprove the operation, the fact that the operation is a binary operation, which essentially means that the operation under consideration is not a binary operation. So since we have to disprove it, it's sufficient to give just one example where the given situation does not work out. So what we do is, we take two elements, 3 and 5, which definitely obviously are elements of the set of natural numbers, since we can count 3 and 5, and essentially they are both positive integers. So we take these two elements, 3 and 5, from the set of positive integers or the set of natural numbers. Now what we do is, we perform this binary operation for these two elements that we have taken under consideration. So let's go back to the definition of the binary operation as per the question. So it says A dot B is A minus B. So they subtract the second number from the first number. So since I have taken 3 and 5, of course I can go it the other way around as well. But in this case, we have to take 3 as A and B as 5. Why? Because if I take 3.5, then by definition 3.5 equals the first number minus second number, which is 3 minus 5. That gives me 3 minus 5, which is minus 2. Now, since I have mentioned before, natural numbers is essentially the set of positive integers minus 2 is not an element of natural number. Minus 2 essentially is not a natural number in its simplest sense. So what we have is, if I take two numbers 3 and 5 from the set of natural numbers, and if I apply this operation as defined in the question, I do not get a number which belongs to the natural numbers. So this fact that A and B, when operated upon, give a result which belongs to the set of natural numbers, this condition essentially does not hold, which means this operation is not a binary operation. Now, I just mentioned that I can take the other way around as well. That is, I can take 5 to be the first number and 3 to be the second number. What happens is, if I take 5.3, it becomes 5 minus 3, which is 2, which essentially is a natural number. So it is a condition where the situation holds, but that does not necessarily imply that the operation in general is a binary operation. So we need to take an example such that this operation cannot be called a binary operation. So that needs to be kept in mind. So here I want to write that we need to take an example such that the situation does not hold. So that will help us to disprove the fact that this is not a binary operation. So that's how we can do the sum. The next sum that we have is A star B is half AB. So if we have two elements, A and B, which are this time defined on the set of rational numbers. So Q is the set of rational numbers. So in this case, instead of N, let me just remove that. So yeah, eraser. So instead of natural numbers, this time we'll be considering the set of rational numbers. So Q defines the set of rational numbers, and we'll essentially be talking about all those numbers which can essentially be represented in P by Q form. So that's how we define rational numbers. We'll probably in a future video look more into the set of rational numbers and set of real numbers, set of irrational numbers. But for the time being, it's sufficient to know that the set of rational numbers is numbers which can to some extent be in a simplified way, can be represented in P by Q form. So let's look at the second sum. As I had said from the sum, A star B is defined as half AB, and A and B are both rational numbers. So we take the same procedure as used before. What I do is the first part of the sum, which says that the two sets, or essentially the set under consideration, has to be a non-empty set. Here the set of rational numbers is by definition a non-empty set, so that a part of the definition is cleared out. The next step is, again, we need to see whether for every element in the set of rational numbers, the resultant of A star B, that is half times AB, is a rational number or not. Now here I want you to do an exercise. What I want you to do is multiplication is a binary operation on rational numbers in general. So since it's a multiplication, what you do is just by the basic procedure that I have shown in the first part. So you take any two numbers, A and B. This time you do not take an example because you need to prove something, so you need to do it generally. What you do is you take any two numbers, A and B, from the set of rational numbers, and if you multiply them, that's if you do AB or BA, irrespective of the order, you will find that AB will always be a rational number. So if it's P by Q, let's say A is P by Q, and let's say B is X by Y. So P by Q times X by Y will be PX by QY. So let me just write that down. So let's say A is P by Q. And of course, which means that A is a rational number. Next, what you do is, let's say you take another rational number which can be represented by X by Y. So if you multiply A and B, you'll get PX by QY. So you'll get PX by QY, which obviously essentially means that it can be represented in the P by Q form. So obviously any two numbers, any two rational numbers, which when multiplied will obviously give you a rational number. So that is what we say multiplication is a binary operation on rational numbers, set of rational numbers. So that's essentially, again, I asked you to prove it and I proved it myself. So anyways, so here I have done essentially the same thing. What I've done is I've again added another, or rather multiplied, or a factor of half. And since since multiplication is a binary operation on the set of rational numbers, half AB, which essentially is a form of multiplication, or a more sophisticated form of multiplication, or a more complex form of multiplication, is obviously a binary operation. So here we see that the definition of the star operation that they have given is a binary operation on the set of rational numbers.